then without, because we see the black hole all of the time. So one of the main difficulties also with our old data set, with the tech data set, where you just have the stars and not the black hole, is a slow motion of the reference system. So we reference ourselves to the meso stars of Mark. And so if you have, so this is probably the difference, the relative motion of the reference frame between the UC and ours. In interferometry, we don't have that anymore because we see the black hole. Now we are on, you would say, systematics on interferometric level, but here it's actually a key measurement if the objects are clean enough, because the quantities which we have are, like with you, we have a wavelength, we have a geometry. So lambda over b is a good quantity. So it would be, I don't see it that we can do something really wrong here.
Okay, thanks.
That's for you, all the way up there. If anybody's willing to run, thank you.
This is indeed a great time to be alive. Watching the accumulation of stars that you have, I wonder at what point do you have any sensitivity towards detecting exoplanets, hot Jupiters, and so forth?
Well, we already do. So we have about 10 exoplanets directly detected, maybe for 6 of them with very good spectra. It's already gone. No, I think we have the best spectra of massive hot exoplanets, literally. So we have spectral resolution of 4000. We can measure the CO ratio for one of them. It indicates really more that we have planetesimal enrichment. So even for the massive gaseous planets, it's not so much senior. I think this is because we are a bit remote from the US, especially our exoplanet community, but please look it up. I think it has a very bright future. Again, it's a very keen signal. It's like a login amplifier. The fringe speed at the exoplanet is so clearly to distinguish from the star. It's wonderful.
Thank you. Yeah.
Didn't quite understand your comment on the stars contributing to the spin of Sagittarius A star. Went a bit too quick for me, because of course, when we see the rotation of the flares, we actually probably seeing the rotation of the gas, not the spin axis of the black hole. So these are very different things. Also in simulations, you see that you're really measuring not the spin axis of the black hole, but the spin axis of the jet and the disk. So I mean, what builds up the spin of the black hole is a completely different process, which happens over billions of years, while we see something that's happening over last hundreds of 10,000s, millions, I don't know, years right now. So very different time scales, really.
Mm-hmm. But still, we have a few fundamental questions, I think, still to solve astrophysically. What is truly the dominating the energetics very close? Is it a spin? Is it the magnetic field? Is it the matter? And do we actually build up a high spin? I know from our images in M87 and Sagittarius A star look very similar on the image, but in my mind, they probably look very different if we could fly there. So for me, the galactic center, certainly the galactic center is quite a massive things with matter flowing in, with magnetic fields. The black hole not so dominant maybe like in M87 for the whole region around.
Right. You need to accrete 3 times the mass of a black hole to actually change its spin, typically, right? So it's and that takes a long time in the galactic center. So spin measures really long-term evolution of angular momentum in the Milky Way, while the accretion is a really short-term developments in our galaxy. And so that's the messiness we see now in the accretion. In the spin gives us also long-term stable.
Exactly. This is what I say, that the flare is the accretion, and the stellar orbits will give you the spin.
Okay, I'm going to let the two of you take that offline. Maciek, you get the final word, and then we're going to move on to Jim.
Thank you so much. I have a two questions, but one will be extremely short, possibly. So question number one, do you see, is that true that it seems that the periods are short with respect to the size of the orbit? So you consistently do see kind of super Keplerian motion, and do you have an explanation for that? It's not expected if that's a part of the flow in GRMHD simulations. It's usually sub-Keplerian in this inner part.
Absolutely. So normally,
I'm very sorry. I will just ask the second one.
no, you are okay.
And the second one would be just kind of very qualitative. How confident are you in this position angle of the angular momentum of those hotspots on a plane? Are you totally certain, or could it be like maybe 90 degrees off?
Okay, for the first one, quickly, so you're right. We see superluminal motion. We do not have a simple explanation. Indeed, we would expect the other way around from the pressure gradient. There are some models which would predict it. If you tie, so to say, your current sheet farther in, you would see the angular velocity from farther in, but at a larger distance. So I think from the French Cerruti or so, there are some of those pictures around. I don't know. I think this is clearly to be sorted. Also, how much of instrumental uncertainty is in that. The other thing was on position inter. You have seen the four. You have seen the four flare motions. I would say they are all consistent with that. Could also be my picture could be very different from flare to flare. So the co-adding of the flare could also be limited by the physics being the same each time we see this energetic event. If it's the infalling angular momentum, it might change from case to case, absolutely.
All right, let's thank Frank again.
Thank you very much.
Our next speaker is Jim Moran. He's going to be talking about some of the historical sort of background of VLBI and giving us some perspective. Take it away.
I recall that my first visit to Granada was in 1984. It was one of the very first conferences on submillimeter astronomy ever. And I presented the proposal to build this instrument called the submillimeter array. So I'm glad to be back for my second visit now. So we have my official title at the top and my real take on what I'm going to talk about in the middle. My takeaway message is that I think we still have a lot to do to achieve super resolution in our images, and more important, to sell that to the general community of astronomers as to what we have done. I'd like to begin with a tribute to Fred Lowe, who left us much too early in his career. He was a real pioneer in the, he was a real pioneer in the investigations of SgrA star, which lasted 30 years. He did the very first VLBI experiment on SgrA star just less than a year after Brown and Ballack discovered SgrA star. He had one baseline, 160 kilometers at the 3.7 meter wavelength. And here's an image of his, not an image, the correlated flux versus fringe rate. So a very solid detection of SgrA star. And he put a size limit of less than 0.02 arc seconds. And this was before the scattering model was even figured out. Then 10 years later, he made the first measurement at 1.3 centimeter wavelengths and was able to put a limit on the size of the galactic center at less than 20 astronomical units. And if you guys think we are the first to get this enormous press attention on SgrA star, back in 1985, Fred had a full-page article about him in the Time magazine in the US. So people really loved hearing about black holes way back then. Notice we now think SgrA star is not quite as hungry as we thought then. And then things progressed rather rapidly. The first VLBI images came along in the 1990s with the VLBI being coming online. And by 1998, Fred Lowe and then other people, Backer, Bauer, Shen, Grisham, first saw that they could detect the actual intrinsic size of SgrA star emerging from its scattering cocoon. So Fred's career spanned an important range of 30 years on all of this. So the second tribute I want to make is to the real father of our craft, and that's to Albert Michelson. And he would have fit right into the ngEHT project. He picked up on the idea of Fizeau, that you could see fringes on the stars, and he made the first demonstration of this by putting 2 slits on the non-Hamilton Lick Observatory, and he measured the angular diameter of Jupiter's satellites in 1891. This is an interesting excerpt from his paper. This is actually the airy pattern of the moon of Jupiter, and then when he puts 2 slits on it, he saw the interference fringes. It doesn't say, but I think this is just a sketch, because back in 1891 they didn't have rapid photography, so this could not be a real photograph of the fringes or the airy pattern. So I think it's just a sketch. But the important thing is that Michelson appreciated the full Fourier theory behind the contrast ratio in these fringes. And he worked it all out. And here you can see something that's obviously familiar. This is a Fourier transform. It's real because he was only talking about symmetric objects. This is really a 2-dimensional integral because this phi function is actually the strip integral, which takes out the 1 dimension in the source. But you'll all recognize the plot that is in his paper of our familiar Jink Bessel function. My fingers are so big and this is so small. You'll recognize the Jink function and Bessel function that we use so often to figure out the size of sources from fringe visibility. One amazing mystery to me is that Michelson completely understood the theory of Fourier transforms. He was actually a key to discovering the Gibbs phenomena. But he never uses the word Fourier transform in any of his optical interferometer papers. It never appears, and I've looked carefully. And the other interesting thing is he must have had a lot of other things to do, because after he did this experiment in 1891, he didn't get around, quote unquote, to measuring the size of Alpha Orionis until 30 years later. He let this brilliant idea just rest for 30 years. But so then you can see what we all know about his experiments on the Hale telescope, the Hooker 100-inch telescope. And this is his contraption out in front of the mirror, the large mirror of the Hooker telescope, where he had his small mirrors mounted, which brought the light in to a central place. And the interesting thing I want to mention here, here's his Fourier transform rendered into the one-dimensional strip integration form. But he thought about measuring not just the size of the stars, but he was aiming to measure the limb darkening of those stars. So here's n equals 0, a uniformly illuminated star, the intensity versus angle. And he considered that, and that gives you our familiar Jink function response. But he also considered tapered responses. And he figured out their Fourier transforms. And it's given by these, and the ever reduced amplitude of the bounce and the visibility response. So he was prepared to measure these complex models. And of course, if he had considered limb brightening, he would have been essentially doing our problem. So as I say, he would have fit right into fitting visibility. So of course, he never got that far with his actual measurements, only measured the angular sizes. So moving forward to the radio case, Ryle and Vonberg connected two antennas corresponding to Michelson's two slits. And curiously, they characterized this two-element interferometer where they added the signals as if it were just a single antenna with this as the gain pattern of the single antenna, which has all these peaks, which we think of as the fringes and the deep nulls. So they took this two-element interferometer and let the sun move through it, and they measured all these sinusoidal oscillations or fringes as the sun moved through the beam of the interferometer. The important thing I want to point out is in the text, Ryle says, an alternative method was therefore used, analogous to Michelson's method to determine stellar diameters. So there's a direct link from radio interferometry back to Michelson. So it's interesting, a lot of people refer to the so-called Van Sittert-Zernike theorem as our intellectual roots. But those guys were working on the side in optics, and it was never any influence on what radio astronomers did in terms of forming interferometric images. So moving on, the resolution of the first radio source was done by Jensen. Oops. Stealing my show here. The work of Jensen, who we mainly associate with his brilliant invention or discovery of closure phase, but his PhD thesis was to measure the size of the radio source Cygnus A, and it was already known to be elongated in the early 50s. And so he set out to try to see what the actual structure was. And here's Jodrell Bank. So he charted a baseline along the axis of the extension known for Cygnus A. And he patiently measured the visibility as he went on longer baselines. So he first went to station 8. This was a known data with these X's. He got to station 8 and he measured a visibility. This is a visibility squared, by the way, because he was using an intensity interferometer. So I noted the square of the visibility dropped to 0.5. And he had a few beers at a local pub and then moved his antenna to station 4 and the visibility went down, moved it out to station 6 and it had gone through a null and then it went up 7 and then down here. So that by the time he had finished station 9, he had his key result that there was a null and there was a nice bounce and going towards another null. And so this bounce exceeded anything you could get from Bessel functions and ring type structures. And so he settled on the explanation that he was seeing a double. So this should have been a cosine wave, but the two components of the double were resolved, and so it didn't get back up to unity. His choice of modeling it looks a little strange. He modeled the source as 2 boxes separated by 1 minute of arc, but I show this in detail because it resembles what we did on the EHT. We slowly, and all the previous earlier interferometry measurements, we slowly increased the baseline in wavelengths until we really got down to where we could resolve the source. And of course, as we know, things got better on the Cygnus as time went on, and we ended up with images like this. So let's talk about the limits of angular resolution, which apply to far field, any measurements in the far field with an electromagnetic detector of diameter d. There is a so-called diffraction limit, which we all quote. I'll learn slowly. We all quote as lambda over d, but there's a coefficient in front of that. And I've always had a hard time keeping straight what this value of A is in front of a lambda over d. Of course, we'd like to make that as small a number as possible. And the smallest you can do in classical Fourier transform theory is to have a uniform UV coverage out to a maximum baseline D, and then you get a point spread function with a full width half maximum equal to 0.71 lambda over D. And to me, that is a fundamental stake in the ground in terms of resolution with a electromagnetic system. Then if you have a single antenna with a uniform aperture in the electric field, then the full width half max is 1.02 lambda over D, and that's the classical Airy pattern discovered in 1838. Then Rayleigh reinterpreted this, just taking the Airy pattern and going not to the full width half maximum, but going down to the first null. And then you get this thing that's in every textbook, 1.22 lambda over D. If you have a linear taper in the electric field, which is typical of a real telescope, then A is equal to 1.27. And that's the origin of the rough approximation that the resolution of a radio telescope is 1.2 lambda over D. So I'd like to quote, as other people have probably said also, but our friend Ramesh Narayan says repeatedly, to beat the diffraction limit, which is 0.71 lambda over D, you must add some external information into your analysis process. And those typically are non-negativity. This is absorption you're talking about. The image has to be non-negative. In our case, compactness is very relevant. You could have edge constraints, like if you're observing a planet, you know, the emission is confined to the planet. You can apply a constraint on smoothness and a constraint on entropy, for example. And all this is, these are wrapped up into what our team in regularized maximum likelihood is doing with all these constraints in there. So the extreme extension of all these constraints is to go to so-called model fitting. And there you can get arbitrarily high, quote, angular resolution. The uncertainty in any model parameter will be equal to the fraction limit divided by the signal to noise. So you can quote angular sizes or angular separations to arbitrary accuracy depending on a signal to noise ratio. So the first map of a sky was made by Grote-Reber in 1944, where he mapped the distribution of radiation along the whole galactic plane. And there is our Sagittarius A source, which was visible in its first map in 1944. Now, the obvious question, if you have a map like this, is can you sharpen it up and try to make it look like it has higher resolution? And the answer is you can do this to some extent, but I think in the late 1940s, people really didn't have the idea of just how important the diffraction limited was. And there was somehow this idea that if you had infinite signal to noise ratio or very high signal to noise ratio, you could arbitrarily recover the small angular stuff, 5 minutes, okay? This was even tried in a method called the method of successive substitutions. The idea here was that you had the true image, I, you had the true image, you have the true image at the top, I, you have some approximation, and then you have what you actually measure, the dirty map, and we have the point spread function of the telescope and its Fourier transform. So one measure of how well you're doing is to take your measured image and subtract from it the convolution of your antenna with your approximation. So what should you use for your approximation? Well, if you let your approximation be your actual measurement, then you can make a first approximation of a restoration. So image 1 is equal to the measured image plus a correction term, which is the measured image subtracted with the convolved version of your model, which is the measured image itself. Then you substitute that into the second level of restoration and get a second improved restoration. And you continue on until you get n series of restorations, and you get something that expands in this binomial term like this. And they tried this, and it actually worked to some extent to try 2 or 3 iterations. And they thought they were really making progress. It was limited by signal to noise ratio. It was this brilliant guy, Ron Bracewell, who entered the scene about this time and wrote this paper, Aerial Smoothing in Radio Astronomy. When I saw this paper when I was a first graduate student, I fell in love with Fourier transforms and have never fallen out of love. So I really encourage you to look at that paper. He showed that this sequence actually did not lead to the true image. It led to the, in the Fourier space, it led to the Fourier transform of the image, but divided by the Fourier transform of your point spread function. So it actually just restored all the Fourier components that you had measured to their proper level. And this gave you the sense of sharpening your image. Now I want to turn my attention to the VLBI results. You've seen this many times the past few days. Here's our visibility curves on M87 and the galactic center. I think it's fair to say, especially in hindsight, if you look at this, the curve, and you see two nulls with a bounce in between and not too much variation in orientation of baseline, that you've really got a, you're really talking about a ring annulus. And this was clear in the data that we took in 2013, that it was probably going to turn out to be a ring. And another analogous group here is Rosalind Franklin looking for DNA. And this is her famous image of so-called photograph 51, the diffraction pattern of DNA. So this is her X-ray crystallography technique measuring the Fourier transform of the two-dimensional projection. And it's got this characteristic X. So to make a long story short, one of Franklin's colleagues stole this image and not stole this image, he showed it to Watson and Crick, to make a long story short. And Watson and Crick looked at this image and said, aha, it's a double helix, just intuiting it as we did for the galactic center. And it's interesting that there's also, this is actually built up in a series of Bessel functions. So here's Watson and Crick's cartoon. And of course, they had the brilliant idea of figuring out these sugar molecules which carried the code of DNA. Meanwhile, Franklin, she wanted to be very meticulous. And 6 months after Watson and Crick, she published this detailed image, which was called a Patterson diagram, but it's really a Fourier transform image. And here you see the helical backbone structure and the sugar molecules. So that's an interesting analogy to me of what our group did. We knew it was an annular ring, but we put in an enormous effort to make the analysis to really prove that it was an annular ring source. Okay, just a minute here. And just to show you how models reveal the structure, here's a figure from Bracewell's book. I encourage you to run out and buy Bracewell's book on Fourier transforms if you want to really get a good handle of what's going on. But if you have a ring, the Bessel function peaks go like this. If you have an annulus, you start seeing a big difference after you've had about half a dozen peaks here, subpeaks. So you're beginning to really show the annulus when you have a fringe spacing equal to the thickness of the annulus, and it departs dramatically. But if you go back here, you can start to see the significance difference very close in. So if you have high enough signal to noise ratio, you can deduce that you're looking at an annulus with just very little data. I wanted to just mention another case of model fitting. Frank just showed us this image over on the left here. We have the blob orbiting SgrA star with the our donut inside here. This is a perfect example of the power of model fitting. They actually centroided the fringe position, and that's what they're tracking here. Their actual diffraction resolution was 3 milliarc seconds, but they were able to measure the centroids of the emission down to 50 microarc seconds, a factor of 60. So I was a little bit annoyed at Martin Rees, who made this comment, which sort of conflated true resolution with model fitting, centroiding. And my final example of super resolution, which is really centroiding, is just the Nobel Prize in chemistry, which was awarded in 2014 to Betzig, Pell, and Moran. And what they did was really brilliant in terms of the physics experiment, but it really came down to model fitting. So here was their image. Here was their image in the microscope, and it has all these airy patterns overlap. This was the true molecular lattice they were looking at. And so their idea was they could turn on one molecule at a time by a method of fluorescence excitation, which caused each molecule to give off stimulated emission by itself. And so they patiently tracked and made a, I don't know if you can see this too well, but they actually made a diagram of all the position points. And this is called super resolution, but it's actually just model fitting. So it's just fun to read Eric Litzig's comment from his Nobel Prize about what he did. I'll just read this. All these things about near-field microscopy together took two young and innocent guys like me and Harold in 1989 and turned us into two stressed and worn down guys. So I said, screw it. I'm sick of science. I really hate academia. I quit. I really had no idea what I was going to do. Next, a few months later, I walked my daughter, Mr. Holden, and hit me. You could come up with a different far-field way of doing super resolution imaging. The idea is that if you have a bunch of molecules that are too close together and their diffractions, limited spots overlap. However, if you can find some way which they differ from one another, it can be anything, and you can isolate them in a higher dimensional space. But once they're isolated with this fluorescence technique, you can find their centers of each one of the diffraction limited spots to much better than the width of the spots, and hence you plot all coordinates of the molecules. I published this idea in 1995. So it was a brilliant work, but it really what it came down to was model fitting. So I leave you with my takeaway message that model fitting is relatively easy, and it's clear to the reader what you are doing. If you're trying to do true imaging beyond the lambda over d limit, you must be very careful. Jose is staring at me intently here. It's driving me crazy. Don't be so critical. I applaud everybody who's working so hard on these algorithms for super resolution. But I think as important as developing the algorithms and doing all these tests we're doing, you really have to figure out a way to communicate with the general audience as to exactly what constraints you've actually put into the soup to get the results. For example, the method of maximum entropy was very popular in the 70s and 80s, but I think it was forgotten. And the reason it was forgotten is because it wasn't clear what the added information was. Why should we be maximizing this thing called entropy? What was a real physical basis of that to our problem? So thank you for your patience.
Jim, you have exceeded your question period. Yeah.
Sorry.
That's thanks, Jim. So Sarah needs to set up. So I'm going to entertain one question. And in light of that last quote, I would particularly love the question to come from an early career person who is not yet burned out and ready to say screw it. So are there any junior folks in the audience who have a question for Jim? Okay, senior folks, mid-career folks, all you folks. Yes. Michael, I don't know if you qualify, but yeah, okay. You're one of those folks.
Jim, that was fantastic. I'm so glad you mentioned gravity, which I think is this triumph of super resolution inference. And so you sort of set this up, but you didn't comment on, do you think it's possible for the ngEHT to make credible super resolution claims? Or do you think that the models are just so complex and poorly understood that there is always going to be uncertainty?
Well, of course, I have to be optimistic. So I'll say yes. But we're always mixing in the model at some level. You either put constraints into the imaging algorithm, and then you model fit afterwards into everything in the model fitting. So I think it's a mix of flowing back of where you put your constraints is, either in the imaging or the direct analysis of visibility or the images themselves. But keep up the good work.
All right, great. Let's thank Jim again. Our next speaker is Sera Markoff from University of Amsterdam, and she's going to be talking about connecting some of the beautiful VLBI work that you've been hearing about over these last many sessions to the sort of broadband view of black holes.
Okay, I have this on backwards. Sorry. Hi, everyone. This was a tough act to follow, but I'm going to try to combine some of the elements of both of the talks we've heard before into a discussion about what we gained from looking at VLBI together with multi-wavelength. And as you've heard from Jim, of course, there's been a long history of the development of this field. This is not VLBI, but VLA of one of the most famous jet systems. And then here you have the VLBI inset. And the development has pushed us for a long time to being able to understand slowly and surely the structures and the dynamics of these systems and moving closer and closer to something like the event horizon. But for a long time, the development was really kind of a parallel track, and we didn't have information from other frequencies, mainly because we just didn't have access to smaller scales. And that is starting to change, especially in the last, a couple decades with precision instrumentation that's been launched into space and ground-based. And I'm going to be coming back to the gamma rays as well, which used to have zero spatial resolution, but now we're actually getting to the point where we can start to tell apart different parts of the system. We can now look at the same, okay, something's not working with the pointer. Can somebody give me a hand here? It's like blinking, but it's not. Okay, thanks. Okay, but now when we, so going from this view to this view, we can now see that there's this glorious multicolor images and these systems, going from the event horizon, what we'd like to understand with millimeter VLBI, if we want to understand the larger system and what this is bringing, to the universe, the kinds of effects that black holes are going to have, we have to understand all the different elements, and these multi-scale objects are by definition multi-wavelength. And so, we're going to be hearing more about this from Priya, but black holes, of course, play an extremely important role in like cosmology, the evolution of galaxies, and we think that energy that's being unleashed by the black hole near the event horizon is basically affecting the largest scales. But for us to understand this, we have to basically work our way inwards to the smallest scales. So these big picture questions that we have about, accretion, how much matter gets down to the black hole, how much grows the black hole versus actually, escaping, comes into accretion physics. How do the energy get converted into other forms and launched out in these outflows, and the role of magnetic fields and the spin of the black hole in this picture? How does this all work? These are sort of the VLBI aspects as we move closer to the scales where, the action is actually happening with millimeter VLBI. We want to start to combine this with what I would consider almost even smaller scales, which is the particle scale, because as we get down to the particle level, of course, that hasn't, the content of the jets has an influence on the polarization of the jets, but also it's actually particle acceleration, which is giving us the light that we see. And this is a really important thing. I'm going to be focusing my talk mostly on this point because particle acceleration is effectively the loss term. If we want to understand some sort of, thinking of jets as almost like conserved systems, and that there's energy coming into the black hole and then being launched into these jets and then somehow making it out to these larger scales, well, we can give Priya the answer she wants, which is, how does this affect, these larger scales, we have to understand the dissipation. And particle excitement seems to be connected with dissipation in the dynamical structures that we can see with VLBI. And we want to try to connect these two dots basically together. And of course, whether or not they're hadrons is another really big part of this question, because if you're trying to launch a jet up to relativistic speeds and it's full of protons, that's going to be a lot more energy than if it's a light jet. Really, to solve these kinds of questions, we need to start to combine VLBI imaging with multi-wavelength observations. And that's basically the point of this talk, is how we can start to do this and have been starting to do this with EHT and where the future is going for this. Now, of course, there's a new dimension, which is multi-messenger, and that in the last few years, there's been associations of flaring AGN with neutrinos events that are coming from IceCube. But this is very statistical associations. And the question is, are AGN really the sources of these particles, and where are these particles coming from? And so this all ties into a longer term evolution and question in the field about how these jets basically convert their energy into particles and the light we see. So I have my own historical musings to go with Jim's as well. And I wanted to say a little bit about the history of how we came to this idea of the multi-wavelength jet that we see a lot in the field today. And it really does go back to already early combinations of VLBI, of course, centimeter VLBI, so not as high resolution, and multi-wavelength flares typically in the optical and the gamma ray. And this is a beautiful paper by Alan Marshall and company in 2008, but looking at the canonical V-source BLX that defines the classification of BLX, they basically were following ejecta with VLBI and seeing that when these ejecta sort of seemed to smack into something that looked like a steady shock, there would be these flares. And so this idea is kind of a tomography to map out the system, has grown in the field that there's a acceleration and collimation zone where the jet is basically, kind of laminar and not dissipating a lot of energy, at least not into the high energy particles. And then suddenly something special happens. This is associated with the millimeter core. So that's of course interesting for us with EHT, but it's really far from the black hole, like 10 to the 5 gravitational radii away. And follow-up monitoring over decades by the Mojave Project for this, and this is the same source. These are the little blobs coming out. There's the black hole, and this standing shock seems to be a real thing. It's actually offset from the black hole. And in fact, we've seen this in many other sources now, we being Mojave. But here's the sample, and of course, here's M87. And you can see that this is in log of the Schwarzschild radius. Again, very far from the black hole, you have this seemingly dissipation region where supposedly something interesting is happening. And the question is, what sets this dissipation zone, and how can we use this to start to, build better models of energy going from event horizon out to these larger scales and some dissipation along the way. This seems to be kind of associated maybe with the Bondi radius, which is the gravitational sphere of influence of the black hole. And that makes sense in a way that the density distribution is going to change at that point, and that might give you a reason for the jet to have a different expansion characteristic and basically maybe expand faster and correct itself, and you get something like a recollimation shock. That's the idea. And that gives you a really good explanation for why you would get particle acceleration. And our colleagues in EHT, Keiichi Asada and Masa Nakamura, have also shown this is M87's radius as a function, the jet's radius as a function of distance from the core, that there seems to be this parabolic, acceleration collimation zone, just like you would predict, changing into a conical flow right around the Bondi radius. And so all this picture sort of nicely holds together, and that would be associated with HST1 not. But, like all good things, there's some complications here, and I'm going to come to that in a second. But this idea of some sort of special zone in the jet really has dominated the multi-wavelength fitting of jets for the last decades. And there's this idea of the single zone that basically you can get away with modeling most of the data, at least from the optical upwards, by just taking what physicists call a spherical cow and sticking it somewhere in the jet. And basically you can fit most of the data pretty well with this. And of course, it doesn't do a great job with the radio and the VLBI. And the question is, what's going on there? But if you're interested in the major dissipation, this is something that can really help you learn something about the particles. It's a bit disconnected though from the dynamics, and that's been something of the problem. So the story does seem to get more complicated now. There's more recent results by Yuri Kovalov and others that are showing that actually, in fact, several of the jets seem to have this break from conical collimation to, or sorry, parabolic collimation to conical at a radius that's much smaller than the Bondi radius. And so the question is, what's going on closer in? Is there something else that's setting the scale? Where's the dissipation into particles happening? And this, of course, is where EHT is going to be playing a really big role, because as we can start to look inwards into these scales for the first time, we can maybe look for features and try to understand what's creating the particle acceleration, where is it exactly happening? And I'll say a little bit more about why that is so important. And the fact that this is sort of moving inwards is also interesting, because if you move away from the spherical cow and you fit full structured jet models, this is some multi-wavelength modeling of the source PKS 2155, famous blazar, and each one of these curves is basically a flare of the source. Now you can fit this, just assuming that each flare is a completely different entity. This is effectively the single zone type of approach, and you have 1 million free parameters. It's very difficult to constrain the physical properties. But if you look at this dissipation parameter, that's just this one. This is sort of saying where the size, where this is happening in the jet and the size. It's all over the place. You know, it's like 1,000 plus or minus 500 gravitational radii. But if you start to think about this as going in a prior, that your jet is a larger structure, dynamical structure, and that there's some action spot, and you model this consistently using all the multi-wavelength constraints that you have, you find that, and I won't say too much more about the details of this, but you basically converge on a radius that is consistent with what is starting to be seen with some of the VLBI experiments as well, but it is further in again than what you would think from Bondi. So the question is, what sets this radius? And is this something that we can connect to, for instance, you know, magnetohydrodynamical flow, something we can predict? And so this is an interesting problem. Now, the other part of the complexity is that ever since the Whipple Observatory in the 90s, we've known that there can be even intraday variability in the gamma rays. And so if these gamma rays are the tracers of most of this dissipation, and you take that time scale literally, then this is actually smaller than the Bondi radius or the Schwarzschild radius of the black hole. So either you get this bifurcation that this is happening in small structures further out, but not, you know, some little turbulent region, or this could be maybe in the magnetosphere of the black hole. And so there's a lot of competing theories. And so localizing is understanding, and that's going to be part of the main theme here. So of course, with EHT, you know, we're starting to try to connect now in the expansion towards the future, this beautiful image with the base of the jets. This is from the white paper on ngEHT. And we also want to understand, you know, how this region sets, you know, the scale for this inner part of the jets where we think a lot of this dissipation is happening, and understand and basically track and follow the energy. But in order to do this, of course, that's just one frequency. And even though these images are great, we need the other information. So we want to pair these. And if we can see variability, particularly in the gamma ray, we want to look for it in these images and start to really answer these questions once and for all. And so for the rest of my talk, I'm really just going to be kind of going through a little bit about the practical things that we've been doing, and the past, sort of moving into the present and work in progress. So you've heard all about the canonical image that we took in 2019 of M87, but maybe not everyone's aware that there was a full multi-wavelength campaign. This is what we do in the multi-wavelength working group that Daryl, Haggard, and I, and Kazuhiro Hada co-coordinate. And this is a snapshot in all the colors of what this system was doing from the event horizon out to the largest scales. And we were really, it was a pretty big deal to be able to get this image, as you've heard all about. And so we weren't so focused on the multi-wavelength at the time of these papers. And in fact, these constraints weren't used that much. We added up all the light to come up with the bolometric luminosity. And we said, well, the power in the jets in our models has to at least be that much power. And then we could compare that to our simulations. And so there's a pass-fail table in the paper. You can see the jet power. This multi-wavelength constraint actually turned out to be a very stringent constraint, ruled out a lot of models. In fact, all the spin equals 0 models. But the spectrum itself, we hardly used. We didn't have non-thermal particles in our simulations at the time, so we couldn't really compare to a lot of the high wavelength. And so we used the X-ray luminosity as a kind of binary pass-fail, but it was hardly used at all. However, we really have an amazing constraint here. And that's what we're starting to do in the coming period is we're going to be trying to get our simulations to be able to fit both the images and understand this. And what's interesting is, of course, if you take the spherical cow kind of approach, and this really reveals where the problem is, I think, in this, you could get a beautiful fit, well, more or less, to the M87 data, like everyone does for typical AGN. And you would say that you had a dissipation zone at about 600 gravitational radii. However, VLBI tells us that this is wrong, right? Because with the multi-wavelength campaign that we did from EHT outwards, we can actually tag each of these points and say, this is the upper limit on the size that contains this flux. And so what that means is that basically a sphere that's around 600 gravitational radii should only go through this point and should fall under all of these. And so we have to have a stratified jet. And then we need, to be able to map which pieces of this stratified jet correspond to where the action is happening in the gamma rays. But with one single snapshot, of course, we can't get a lot of information out of this. So the key, of course, here is to try to do multiple observations and to try to track variability. Now, luckily, in 2018, M87 performed, and I'm not allowed to show you the top secret TeV light curves at the moment, but I can tell you we caught a flare, and it was actually the first significant gamma ray flare that was caught since 2010. Now, the sampling, it hasn't been great, so we don't know how common these things are actually, but we can also, from our multi-wavelength observations from Chandra, say that it's happening in the core. It's not happening in the HST1 knot, which would be associated with the Bondi radius, like I was talking about. So there's something interesting dissipation-wise happening closer in. And we're still waiting on the M87 imaging. We just heard about this at the earlier part of the meeting. But as soon as we get the L2 data and the images, we're going to see if there's anything changing there or not. And this can be a real, groundbreaking result for people who are trying to understand the particle acceleration and the dissipation. And so this is in the works at the moment. And of course, the key now in the future is that we're taking our theoretical models and we're using these constraints. This is already, this is work by Christian Fromm's group, but fitting the spectrum with different models. And then the same models also have consequences for the way that the VLBI images are going to look. Now, we're not hitting the complexity yet. There's a lot of important questions. For instance, there's this limb brightening. Alejandro talked about this earlier in the week, that some of you saw this, but there's weird like pinchy features in the 3mm image. We need to understand, is that a dissipation zone? Could that be the reason we're seeing particle acceleration? And so trying to connect all these dots is going to be a really important part for the next several years. Now, you might think, well, why is SgrA star being discussed in the context of jets and dissipation? I don't want to say too much, but you've heard all about the source in the morning, of course, from Frank. And we know that we have these amazing X-ray and infrared flare data. But this turns out to be a really interesting kind of complementary part of the puzzle for us, because we have our ALMA light curves here, and we have, during our campaign, we caught this X-ray flare, which kicked off some interesting variability. And this is something that we're still yet to probe. This will be coming in the upcoming papers. But the X-ray data and the infrared data were used as a really tight constraint. This is a passing model and a failing model. And these are the 200 sort of fiducial models that were used in our paper. And you can see this in paper 5. You heard about this morning, that very few models actually passed our multi-wavelength constraints. So this gave us a lot of information about the plasma near the black hole. But more importantly, these flares are telling us something about particle acceleration in plasma right outside the black hole, which is something we're not going to be able to do to see, in any other black hole. And trying to understand, what do these flares have to do with the jets, or the lack of jets maybe, is a really interesting question. And so the key now is to start, we have models. This is work by Kaushik Chatterjee and Bart Ripperdo and company. We can produce flaring, things like plasmoids in the flow, and try to see how this connects to the outflows. All of our models at the moment for SgrA star that seem to work predict that there's a jet. Why don't we see it? And it may have something to do with dissipation happening so early on that the particles just cool so much that they're not actually able to light up the jet further out. But we also know that this variability was very constraining. It was actually a constraint that we really didn't understand and couldn't model in the first set of papers. But the multi-wavelength variability is also a huge constraint. And we can construct things like cumulative distribution functions for the infrared flares. This is the data here the black line. And these are some simulations, the colored lines are from different simulations. And you can see that it's not only in the ALMA variability, but also in the multi-wavelength variability that we're having some problems understanding these variability signatures. So understanding these flares, understanding the physics is really important. And I just want to mention, this is a complicated plot, but what you're seeing is a two-dimensional projection of a line projection of a two-dimensional plane in a three-dimensional space of the X-ray luminosity, the radioluminosity, and the mass of black holes. And what's really important is that this stretches from stellar mass black holes all the way up to supermassive black holes, exactly the kinds of sources that we're looking at with EHT. And every black hole that is accreting at a somewhat lower rate and launching jets fits on this correlation, except for SgrA. I put it here, but if you do a bit of a more, this is an old paper already, probably deserves some relooking at this, but it seems like the flares are kind of limiting, are building SgrA up towards the plane, but we've never seen a flare so far that actually violates it. So maybe this is a connection of how, the energy and dissipation is connected, and that this could have something to do with accretion rate. We're not really sure, but there's a lot of really interesting physics that's coming here. Now, I won't say much about this, just to flash that we have other papers in the works from the multi-wavelength working group, OJ287, 3C279. I can't do these justice, but I'm just flashing them here, and I encourage you to keep, talk to the writing teams and also keep your eye out for these papers. And there's a lot of monitoring going on of other sources. We've already published SgrA 3C279, and we're going to be working towards the multi-wavelength as well. But what I want to end with is a little bit about the future, again, with this perspective of the thing that I'm, of course, I'm a little biased clearly, which is the Cherenkov telescope array and the connection to particle acceleration, because this is coming online right around the same time as the expanded EHT projects. And it's a two-site, next generation, very high energy, so GeV and TeV gamma ray facility that's going to be orders of magnitude more sensitive, especially for fast flaring. I mean, compared to Fermi, for something that's changing within an hour, it will be 10 to the 4 times more sensitive. So we expect to see a lot of interesting things, and it also has real-time detection. It's able to see its own flares. It can be triggered from outside, but it can trigger itself. And this is a game changer for us. It also has better spatial resolution. So this is the M87 sort of complex. Here's the current generation TeV facilities. Everything is included, and even though CTA will be better, everything we're really kind of interested in within VLBI is within this field of view. However, the pointing accuracy is much better for CTA. And if you look at, this is the pointing accuracy of Hess compared to CTA, basically CTA should be able to tell the difference between particle acceleration happening sort of down near the black hole versus out near the Bondi radius or, at the outer parts of the jets. And this is really exciting. We want to be able to start obviously looking at the same time with these facilities. And then, we can start to figure out which model and which kinds of physics are at work, which also helps us better understand the physical properties of the jet. So this is a very related thing. You really can't do one without the other. And I'll just say, of course, we have these amazing tools now with very high resolution simulations that allow us to actually start to see the types of structures that give us the variability, and we can make predictions and we can try to discern using these campaigns between these different types of mechanisms. So to give you an idea of what I think is coming, this is one of the more extensive multi-wavelength campaigns that was done on a particular AGN, looking at 2 different gamma ray flares, and this is going all the way down to radio and optical and polarization. And it's just the point being that if you look at this flare, you see some very different things, including polarization flips that you don't see in the second flare. So it's a stochastic process. We also know this from SgrA. You don't learn something from one flare. You need to have enough statistics to build up the kinds of probabilistic distributions that you can use to test theoretical models. And that just hasn't happened yet. So you need really like campaigns of weekly cadence over years to be able to do this. And that just hasn't been done yet. But CTA is planning to do this. There's a sample. And so really all we need to do is sort of piggyback on this, but it requires a lot of thought for the development of the array, how we're gonna stage the dynamical scheduling and, a lot of things like that. So I won't go into details of this, but I just want to mention that, if you're interested in this, you can look at the Science with CTA book to read about the sample. Here's sort of a rough plan, But a lot of the sources they're planning, they're going to do deep exposures on 2 of our favorite EHT sources. There's going to be long-term monitoring of many, many sources, 15 to 20 of sources that are very interesting for us, as well as looking at 80 or so 100 other types of sources to look for flares. And if we're phasing up so that we schedule together, we're going to catch a lot of the same activity and have amazing information about this. So there's just a flash that there is a brewing proto project within the collaboration that's sort of cross between jet secretion and the cosmic context group and New Horizons and Transits. I'm sure many more people are going to get involved, but we're trying to take these samples that people like Neil Nagar have been developing and Venki Ramakrishnan to look at what are the potential future sources for expanded arrays, and then cross-correlating this with these interesting sources for CTA, also for neutrino monitoring, and so on, and try to find kind of the golden sample that we can follow, because then we can try to develop the array in the correct way that we'll be able to follow these sources. And I'm basically, that's my summary. I just want to say, that if you really want to understand the big picture questions coming back to this, you have to understand these small scales. And one of the missing pieces we still have is this connection between the dynamics and particle acceleration. And I think that there's just going to be a revolution in the coming years. EHT is already starting it, but as we move towards a population, and actually I haven't even touched on this, but of course transients and small black holes will be important as well. We're going to learn quite a lot, but there's going to be a major challenge to developing these modes, and yeah, hopefully we'll manage it in the coming years. So thanks for your attention.
Awesome. Thank you very much, Sarah. We have time for questions. Yes, I see one from Avery.
Hi, Sarah. That was a wonderful overview of this many splendored view of our favorite sources. I want to ask a question though about you bringing into contact the very high energy gamma ray picture, right, which is so important in understanding the dissipation zones, as you said, and the structural elements. So the one zone models, their greatest feature is simplicity, right? But we know these, as you said, are not one zone objects, and in fact, they span an enormous range in scales, right? So as soon as I allow an external Comptonizing photon bath or an external driver for non-thermal particles far away, everything becomes nearly unconstrained in the standard gamma ray arena. Is there a hope to actually, cover that range of scales here? I mean, we're going to get to the horizon, but we're not going to touch the radio lobes really. So what's going to be, in your opinion, what's required to cover that range of scales observation?
Well, I think it is the combination of imaging and, so the point is, of course, with EHT, we're not going to cover those scales, right? But it's connecting it to the larger scales and then looking at the same time. I mean, it's sort of what I was saying is you somehow need to connect what's happening near the black hole, because our images, right, make a prediction for, or lead to models that make a prediction for the larger scales as well. And we are starting to have simulations that can go out now to 10 to the 5, 10 to the 6 gravitational radii. So we're already able to cover, I would say, the places that now we're seeing that the activity is happening. I think the acceleration areas are favored to be closer in the most recent work for both CTA and neutrinos. There's some interesting mismatches between CTA and neutrino, backgrounds. But what seems to be happening, and this relates to your question about Comptonization, is that it depends on both the luminosity source, but also where this zone is happening, right? And we probably could explain most of the neutrinos and gamma rays together with one consistent model with exactly the EHT type sources, as long as you're above the sort of messy region that you get in higher luminosity sources that would give you a lot of the Comptonization there. So this is work going to people like Palladino and others in Walter Winter in recent years. I think that the potential to put this all together is we don't need to go to the radio lobes. I frankly think the radio lobes are probably not the key source of what we're looking at, because the favored sources seem to be low luminosity BLX and so on. So from my point of view, I think it's in reach for us to do this. We've got the simulations, we've got the, the VLBI going out to these scales. We understand the source term, and all we need is to just look enough to get the variability, enough to build up some kind of statistical pattern. So maybe I'm over optimistic, and I know it's complicated, but I feel like we're finally able to break free, of that single zone model once and for all, right? And M87 is showing us the way for sure. So we have a great test source.
Thanks. Do you have another question?
Thank you for this really wonderful talk. I'm curious to hear more about what you think, these type of jets learn from studies from, stellar mass black holes, X-ray binaries. What kind of synergies are there?
Yeah, so that would be a whole talk, of course. But X-ray binaries, what's really amazing actually is that they have a dissipation zone as well. And what I think is really fascinating is that you can actually see this dissipation zone moving in real time. So X-ray binaries are basically like supermassive black holes for the impatient. I think it was Roger Blanford who said that, right? And so when the accretion disk is changing, we actually see that this dissipation zone moves orders of magnitude. That hints that this is probably some sort of magnetohydrodynamical type of driven thing that we can learn from X-ray binaries and start to apply it to our models for AGN, because a lot of this is self-similar. For EHT specifically, you won't be able to see necessarily those scales, but there's people in the collaboration, of course, Alex Teterenko is one of the main ones, and Rob Fender, who are looking at tracking the blobs from ejecta outwards, similar to what's been done for AGN, but in this case, by actually tracking the motion and the light, you start to break the degeneracy of the total power in a different way completely. So there's another way that we can start to constrain the content and whether there's hadronic content or not, in the smaller jets. So they're actually equally exciting, although I think supermassive black hole people don't think so. They're a little bit underrated, but I think that we're going to be seeing some very interesting things from those as well. Also, especially with CTA, but EHT as well.
Great. Let's thank Sera again. Our next speaker is Priya Natarajan, who's going to give us the cosmic context for all these black holes we've been talking about. So Priya, whenever you're ready, take it away.
Yep.
Hi, everyone. It's a very tough act to follow, being the last speaker in this session and between you and lunch as well. So first, I want to thank the local organizers for making sure that we are all here. And I also want to thank all the members of the science working group that with Jose Luis, Black Holes in the Cosmic Context, for all their exciting input, discussion, conversations. And so today, what I want to do is to try and make a case to you of what the ngEHT can really teach us about some of the fundamental open questions about black holes. And so as you've all seen, the incredible work that has been done on these two individual sources, Sagittarius A star and M87 star. So we know a lot, and Sera just showed us the incredible multi-wavelength follow-up and what all you can learn from the follow-up of these sources. And I hope to make a case to you that having a similar tomographic view across scales with measurements of the accretion rate as a function of radius, estimates of it, measurements of, say, 10 masses and 10 spins for nearby black holes is going to be transformative synergistically with other instruments, other observations that are going to be coming online very soon. So there are many, many open questions that have to do with understanding black hole, supermassive black hole populations, and the buildup of their mass history over cosmic time. So some of the key issues where we have open questions are really seeding, the formation of the early black hole seeds that eventually grow over time via accretion and mergers to give us the supermassive black holes at redshift 0 that we are accessing with experiments like the EHT and ngEHT. But there are many open questions there. Then there's the issue of fueling. And I think, as Sera pointed out, one of my favorite questions, open questions, is how do we relate the accretion rate that we have estimates of at a different radii, at the Bondi radius, as we estimate in simulations. Those are the kinds of physical scales that we can probe in current cosmological simulations. And how do we couple that with what we are inferring as in the accretion rate much further inside the Bondi radius from M87 star and Sagittarius A star data. So I want to touch upon these 4 questions and show you what the models, these are ensemble models trying to understand the growth of a population of black holes over time, and their observational signatures, the model assumptions that go into producing these observational signatures. And so I'll touch upon the formation, the open questions and seeding, and talk a little bit about the current incomplete senses of black holes. And that's relevant because that feeds back into the formation efficiency of the seeds. And then in the end, I want to close with the point that Sera made, which is, bridging scales is really what we need for an ensemble of black holes. So we need data across scales, multi-wavelength data, to take us from near horizon physics to the Bondi radius and beyond. So let me just first focus on some of the open questions that have to do with the growth paradigm. So these are the issues of gas fueling. How much of the gas actually makes it onto the black hole? How much of it is lost in an outflow? And what are the signatures that we can measure for the feedback from the flow onto black holes on a range of scales once again? And we'll talk a little bit about the models, the simulations, and the observations. And the key point that I want to make is that for all this work that spans scales and cosmic time, we rely very, very strongly on local anchors. So correlations between black hole properties and host galaxy properties that are empirically measured at low redshift. And now we have exquisite data for Sagittarius A star and M87 star. These anchor population studies. Therefore, having a range, a sample of sources that span accretion rates, black hole masses, is going to be invaluable. So ngEHT has the possibility to offer us a rich set of local anchors. And I'll show you now that the local anchors at the moment are highly incomplete. So filling in that space of accretion rate, black hole mass, and potentially spin is going to be critical. So the population studies at the moment rely on studies of quasars. So it's an incomplete sampling because at any epoch you detect only the brightest quasars. And as you all know, the abundance of quasars, highly accreting black holes, falls very precipitously at low redshift, right? So, and the key questions that these population studies allow you to access are by creation of these sort of 2 model entities. One is the black hole mass function, and the other is the quasar luminosity function that is actually measured. So the question is, what is the accretion rate? What are the environments of characteristic black holes with given accretion rates? And of course, what we really want to do is add spin, the dimension of spin, to this, because you all know that the radiative efficiency depends on spin, and the spin encodes dynamics, as we'll see, as well as the mass buildup history. So all the current models and simulations that follow, the semi-empirical, semi-analytic models, that follow black hole growth from high redshift down to redshift 0 are anchored at redshift by observational data, multiple sets of observational data at redshift 0. And so what we really need are more reliable, self-consistent local calibrators. And I think this is where ngEHT can be truly transformative for these models. So we already know that there are correlations which we exploit, observational correlations between galaxy bulge mass, bulge luminosity, stellar velocity dispersion, and the mass of the central supermassive black hole. And so all of these correlations actually folds into generating the local black hole mass function. I just want to point out that this black hole mass function locally is what allows you to figure out the number of rings that you are likely to see. By some very nice work by Dom Pesce and collaborators. And so 10 black hole masses and spins are really very viable. And that's why we've sort of been pushing this number. And I hope to show you that, you know, with 10, we should be able to make a really important difference in tackling the uncertainties in the models. So current cosmological simulations that do not actually reach the kinds of scales the EHT and ngEHT observations are going to probe allow you to track gas flows and the formation of stars and the growth history of black holes via accretion, mergers, and accretion, merger-triggered accretion over cosmic time. So what I'm really showing you here is a set of simulations from Michael Trammell and the N-Body shop. This is the Romulus suite where baryons, dark matter, and black holes are followed and their growth history over time, the accretion history. And I just want to point out that in these models, there is an explicit accretion model for gas that is put in at around the Bondi radius. So we're talking about 10 to the 5, 10 to the 6 gravitational radii. So that's really, these are the best state-of-the-art simulations, and that's where we are. So we sort of have a gap into, we have a black box in terms of what's happening inside that we really need to fill. And that's where the data are going to come in to be critically important. So we also have the potential of getting a lot more black hole data across wavelengths for populations from upcoming studies and upcoming facilities. So I just wanted to plug this idea that we've put out there. We've co-located all the observational data and simulations so that you can develop specific machine learning tools for analyzing these black hole populations. So what are we finding? As I said, all these models and simulations are anchored at redshift 0. So you start of seeding, so these seeds of okay. So even though we are anchoring these models at redshift 0, by 3, we are already falling out of line. So it's not surprising Sorry about that. Okay, and of course, we find going further out in Redshift, by Redshift 6, we are completely falling out of line. There is no simulation with its specific independent recipes for feedback and black hole growth. None of these simulations are able to replicate the observed quasar accreting black hole population by Redshift 6. So this is just to show you that the anchors at Redshift 0, if we had more anchors and if we had a range of anchors beyond just scaling relations that are part of the constraints that are currently imposed, we can do significantly better. And that's where detailed ngEHT follow-up of tracking the accretion flow on small scales and coupling, as I'll show a little bit later, with simulations that track the accretion flow over a range of scales is going to be extremely powerful in getting rid of many of these current uncertainties that plague the modeling. So let me quickly go through what our current understanding is in terms of the seed formation at high redshift. And remember, the efficiency of forming seeds is a key ingredient. Independent of the details of the number of physical processes, the number of channels available to form black hole seeds, initial seeds at high redshift, where it really impacts, where the rubber hits the road, is what it implies for the efficiency of that process, because that directly translates at redshift 0 into the detailed shape of the black hole mass function. So at the moment, we believe that largely speaking, there are two sets of seed formation scenarios. One is light seeds that form from the end states of stellar remnants. And then you have multiple ways of forming massive seeds, be either dynamically within nuclear star clusters or from direct collapse of pristine gas. At some level, this distinction between the two seeding channels is somewhat semantic in the sense, essentially, these are models in which you have light seeds that grow gradually versus massive seeds that have very early accelerated growth. So essentially, that's the difference. So it's telling you something about the environments that these seeds could sit in. So there are many additional black hole formation channels, and they, as I said, they all have implications for the seeding efficiency. And this translates directly back into our constraints at redshift 0 and whether and how we interpret the amplitude, the slope of the scaling relations and the scatter of the scaling relations. So there's some very interesting consequences. There are ways to discriminate seed models. And as I said, there's going to be synergy with JWST for ngEHT, with LISA and other future X-ray missions. So this is exploiting all the missions and the data streams that we anticipate having. So some of the optimal sort of sites for the formation, for example, this is just an illustration for the direct collapse black holes, is that you form these direct collapse black holes in the vicinity as in sort of satellites of a galaxy that has had very early star formation, population 3 formation. So one of the intriguing observational signatures of this process is that there is an intermediate stage where you form these direct collapse black holes. They actually merge with this parent galaxy, and you have these obese black hole galaxies for a brief period. You have an inversion of the scaling relation, the same scaling relation that anchors us at redshift 0. There's an inversion, and you have the black hole here. The accreting black hole dominates the spectrum and the mass budget. So the black hole mass is comparable to mass of the stellar component at this epoch, and that is actually detectable by JWST. It's a brief transient stage, but it's actually detectable. There's a whopping clear signal. These plots are slightly busy, but I just want you to note that the detectability is shown in these black hatches here for JW. And the orange curves and the purple curves are just two models for different metallicities for the stellar component that the direct collapse black hole merges with. So there's a signal that's going to pop out. And there are several groups, including Marta Voluntaries at Paris, Rafaela Schneider's group in Rome. We've all made predictions that are compatible, and we all predict that these sort of this critical stage that tells us, gives us key information about early black hole seeding should be discernible and should be detectable with JWST observations. And most importantly, sort of models in which the seeds grow very, very gradually, starting from light seeds. We believe that, you know, at early epochs, so these are plots that are made for sources at redshift 9, they should actually not be detectable. And you might think, you know, why would, you know, how relevant are these observations of very high redshift seeds for, you know, the kind of sources that ngEHT is going to be imaging? So the idea here, as I've been saying, is that you have these population models, and we need to integrate all. We need to have some fundamental ways to connect black hole populations over cosmic time, because they grow and evolve into each other. So there are other discriminants in terms of disentangling, as I said, the many unknowns with accretion and seeding. And there's some surprising discriminants. For example, the occupation fraction, which is the fraction of galaxies as a function of their stellar mass that contain black holes. And that's something that's measurable at redshift 0 in a multiplicity of ways, just by spectral signatures, by variability. And so this is, you know, additional data that is going to come in to anchor these models better at redshift 0, along with the masses and spins that I mentioned earlier. Of course, one of the really clear-cut sort of discriminants is going to be LISA data. And LISA data, you know, the predicted merger rates depend very strongly on the seeding. The orange and red here are for a range of accretion models. So marginalizing over the unknown physics of accretion, you are still able to tell the difference between light seeds, which are the orange ones, and the purple blue, which are more massive seeds. So one key uncertainty that I do want to bring up in all these model building and simulations is the role of dynamics. How quickly do black holes merge? That's something we don't really know. But we know that they actually do merge because we see black holes that have merged, and we've seen black holes at various stages of mergers. So I'll just go over this very, very quickly because I want to spend a bit of time running to the end of my time about the advantage of coupling scales. So here I just want to remind you that in the simulation that I showed you, this Romulus suite, it's a special set of simulations where basically the supermassive black holes are not artificially pinned to the galaxy and halo centers. So you actually detect a population of wandering supermassive black holes. And the reason this is, again, interesting and important is the overall seeding efficiency and the growth mechanisms. They are all impacted by the full census, by having a full census of black holes. And so what's interesting is that 10% of the mass of central black holes by redshift 0.05 is actually locked up in these wanderers. And at high redshifts, say redshifts by 3 or 4, the mass in wanderers is in excess of the mass that you have in the centrals. So these are some very intriguing properties that allow you to detect these populations. So we predict that there are sort of multiple ways of detecting these populations that once again has important implications for the efficiency. So what are we after? What is the deeper understanding that we want of supermassive black holes? So the deeper understanding we really want is to understand the relationship. This is of course in the context of the cold dark matter paradigm, the relationship between the parent dark matter halo, the host galaxy, and the central black hole. And so the parent dark matter halo in all our modeling, be in simulations or these empirical models, is the mass of the halo and the mass build-up history over redshift for the halo. For the host galaxy, that anchor these models and are fundamental to the simulations are the stellar mass, the velocity dispersions of stars, and the scale on which you are taking these models as a function of time. For black holes, the key quantities that we want, but we don't yet have in the simulations for sure, and we are slowly incorporating them into the models, is of course the masses of black holes, which we do have. But what we do not have an understanding of is the accretion rate as a function of radius and as a function of spin. And we, of course, do not have direct handle on the spin through simulations. And as we saw, not directly through observations yet either. And we need all of this as a function of redshift to have a comprehensive understanding, to understand the role of the larger environment, the gas content, and the radiative efficiency. So we want to probe these deeper sort of underlying scaling relations, because it looks like we have collapsed these scaling relations to a lower dimension, and that's what we're really looking at. And you can see that even with the recent work on Sagittarius A star and M87, there's a real diversity of properties that we figured out for just these two black holes, right? So for Sagittarius A star, we know now the accretion rate at a few times the Schwarzschild radius and at the Bondi radius. And it looks, I think Frank showed some really beautiful data where, you know, the stellar winds can actually power this accretion already. But then what's happening to the accretion rate? How much of this mass, gas mass actually reaches down is something, and why, how it's lost is something that we don't really know. So I just want to advertise this ongoing project where we are trying to link these scales by doing nested simulations where the output of a larger scale is going to serve as the input for the inner scale. So we are going to nest 4 zones, which are in which we are going to try to track gas flows all the way from kiloparsec scales all the way down to few times the Schwarzschild radius. What's the quest? The quest is to be able to build models for black holes beyond just these two, which utilize this entire panoply of multi-wavelength data. So this is beautiful work from Sera and her group, just putting together visually, showing you the range of phenomenology that we can measure across wavelengths. So the idea then is to be able to do that for, say, Sagittarius A star. And I just want to show you already people are starting to put these kinds of data together. And these are going to feed back into our models, the kind of model that we can build with a degree of freedom. So here I'm just showing you a recent work. There is the Fermi bubble, the Erosita bubble, and this is in the galactic center, and integrating. So we telescoped all the way in from these scales, which are several KPC scales, where we see energy deposition and signatures down all the way to the work following the orbits of the stars, all the way down to the EHT image. And so the prospects are to, the hope is to get to shadow almost